yesterday, we talked about the magnetization, what the features in the magnetization are, what the various features may correspond to. And today I want to talk about further we talk a lot about strain at the same time. So what I want to introduce is the strain properties, what we get from strain measurements, what we understand from strain measurements as well, and what the technique for the measurement itself is. I had talked about the measurement technique of the magnetization and why we do these various kinds of magnetization measurements under the protocols, the zero field cooled, and the field warming. And so what we had seen was that the zero field cooled and the field cooled provides us information on the frustration properties, perhaps, whether there are mixed magnetic interactions. And any difference between a field cooled and a field warming measurement, well, okay, that gave us the information perhaps on some structural phase transitions going on. So then when we looked at the structure, what we saw was that, okay, we have an L21 state. Out of that we can build our L10, and we can modulate that, and we get these funny structures. And then we came to a point where we said, well, what was happening in the magnetization? Now, here we said that, okay, we had a Curie temperature. Here we have something, we've defined it as a Curie temperature, but it's not a pure ferromagnetic transition because there are all sorts of mixed interactions over here going on, and that's why this is very steep, like in a regular ferromagnet when you measure in a small field, and this is very smeared. It shouldn't be like that. And what is smearing is that, of course, that the ferromagnetism is not stabilizing at one particular temperature, but it's the whole process is continuing over a certain temperature range. And this process is the ordering of a mixed ferromagnetic and another non-ferromagnetic entity, but we don't know what that non-ferromagnetic entity is. We think about it in terms of anti-ferromagnetism. Now, if we go back and look at our structure, what do we have? We come from a high temperature cubic phase to either a 14M modulated structure or a 7M modulated structure or a 5M modulated structure. Now think about this. If I were to try to make a ferromagnet out of this, it'll work, okay? I'll just point my arrows in one direction and somehow I'll find some axis where I can get a ferromagnetic component. So that's not too bad. But if you try to build an anti-ferromagnet here, how would you do that? You can't do it. It's not just not possible. Yeah. Yes, you will have some spins pointing in opposite directions here and there and things, but to build a long-range anti-ferromagnet out of this is not going to be that easy. It will not be that easy, certainly. So what we know, however, is that there's a drop in the magnetization. And in many cases, this can go all the way down to zero. And if it goes all the way down to zero, you don't have ferromagnetism there anymore, yeah? You have some kind of a compensation of the spin so that the net magnetization towards the outside is zero. So we have all sorts of frustrated states. Now, what did we say? We said that, well, this looks like blocking when I talked to you about blocking, and this could be something like a blocking temperature maybe. So, what is the evidence of blocking? What are further evidences that we may have non-ferromagnetic components in here, and whether we have anti-ferromagnetic components or not. And that is what we try to understand, again with magnetization measurements, but other kinds of magnetization measurements. Namely, these are the magnetization measurements that lead to the observation of the so-called exchange bias effect. I'll tell you what that is in a minute. Exchange bias, if you find an exchange bias in your measurements, then you are, it is more or less beyond doubt that you have the antiferromagnetism there somehow, but then you have to find it with neutron diffraction or some other things. But exchange bias actually is a very convincing evidence that you would have antiferromagnetic interactions with your ferromagnet as well. Now, we're going to be coming to that eventually today as well. So, but before going into exchange bias and the understanding of antiferromagnetic interactions and so, we will look at strain just now. We have Martensitic transitions. This involves strains, and it is very appropriate, of course, to study the strain and the strain properties. Strain is a very easy way of measuring things, and it gives you intrinsic properties, because all you have to do is put a strain gauge on something and then change the temperature. If you want to, you can apply a magnetic field, but you don't disturb the system when you're doing this. Anyhow, so we have the Martensitic transition, and then what did we do? We went and sat at a temperature which was close to the austenite start temperature from below, around here. And then what we do is we apply a magnetic field. And when we apply a magnetic field, we see that, let's see, this is 200 Kelvin. This and this, there's slightly two different samples. They're very similar, but the transition temperatures have shifted a bit. So if you're sitting here, then you're probably somewhere around here, okay? So you sit here, and then you turn on your magnetic field, and you find this field-induced transition that you see over here. So you're in one state, and then you go into another state. You're in one state, and then you go into another state. So what is this state? You see here in this state, we said that, okay, we have here antiferromagnetic interactions. But what are we seeing? When we're applying a field, we're seeing first some kind of a saturation that is happening in that area. So it's not a pure antiferromagnet either, okay? That when we're applying a magnetic field, we have a large magnetization here. And as we increase the field, we go into the ferromagnetic state. Now, this we called a field-induced transition, but indeed, to really convince ourselves and to prove that this is a process in which the magnetic field is taking us from one crystallographic state to another crystallographic state, namely from martensite to austenite, is to do the diffraction under magnetic field. Okay? So if you do a diffraction under magnetic field, I showed you this a little while ago, but I want to show you to you now in the light of this. We start in the Martensite phase. So the Martensite phase is in zero field. In zero field, we have these black lines over here, okay? And we have some complex, I think this is 5M modulated structure, okay? The black lines. Now what happens when we apply a magnetic field is at 2 Tesla, you see these blue lines over here. They start increasing, whereas the intensity of the black lines start decreasing. And when you are up at 5 Tesla, you see that your peaks related to the cubic structure have gained intensity. So this tells you definitely that, okay, that you have a structural transition when you apply a magnetic field. So people say neutrons always tell the truth. Yeah? So we have this. Now, if we have a field-induced transition, then we should have lots of strain associated with this as well, because we're going from one crystallographic state with perhaps a certain cell volume to another one. And in the process of doing so, we're changing the volume of the whole thing, and that may be associated with all sorts of strains. So, as you may recall, what did we have for nickel manganese gallium for the shape memory system? We had a single variant where we applied a magnetic field and we grew other variants at the expense of the older variant. And we had a change in length of the sample within the Martensite state. Here there is no field-induced transformation, and the strain looked something like this. So we applied a field, so the sample got longer, and then we removed the field and everything got stuck there. Now, in the case of a field-induced transformation, since we're going from one crystallographic structure to another crystallographic structure, we are again going to have a change in the length, because we're going from, let's say, although it's a modulated state, I'm approximating everything with something tetra. Yes, yes, please.
Arrows are the strain directions.
These arrows you mean?
Yes.
This represents the easy axis. Okay? I'm sorry, I didn't say that. This arrow here represents the easy direction of the magnetization. So the short axis is the C axis. The long axis is the A axis. So C over A is less than 1. And this arrow represents then the easy direction and therefore the C axis. Okay? Since the C axis is the short axis, when we rotate everything in the A direction, the blues look like this. So the C is now growing in this direction because we have a strong magnetocrystalline anisotropy. So the field is selecting indirectly through the coupling of the spin to the structure. It's selecting the C direction as being parallel to the field. So it's getting shorter in the width, but what we're interested in is the change in the length, and the A is a longer axis so that the sample gets longer. Here again, we have, let's say that the C axis is a long axis, is a short axis, and somehow we're switching this around. And when we apply a magnetic field to a supposedly single variant state, we are putting the thing into a new state. We're not growing variants or anything like that. We're coming from a tetragonal to a cubic state. So what is exactly happening here in between, we don't know, but this is the initial state and this is the final state. And we have a length change which looks similar to this, except that this length change is now reversible. They can go back and forth. Here the strains, associated strains, were about 10%. In this case, they're of course limited by the crystallography themselves. Here the strain we measured to be about 0.1% in a polycrystalline material. Still it's quite large for a polycrystalline material, actually. Yeah, we go up and down like that, and if we look at the strain in a magnetic field, this is the strain, and at room temperature, we're in the pure austenite state, in the pure cubic state, so nothing really happens. It just, there's hardly any magnetostriction. Compared, of course, to the strain that we get when we have the field-induced transformation. So we start here, we apply a magnetic field, it goes up 0.14% or something. And then when we remove the magnetic field, it goes back down. And you can reverse it, of course. You see the same thing happening on the other side, and then this loop will be followed continuously. And when we look at the magnetization, here we see the field-induced transformation. We go up, this goes to about 5 Tesla, same as this field over here. And as we decrease the field, this goes back down. So the strain measurements, what do they give us? They give us information on what has happening to the length change, and we see here that everything follows more or less the magnetization. The strain is related to the magnetization almost directly. Now we'll come to some strain measurements. Does everybody know what a strain gauge is? Do some people not know what a strain gauge is? I can't see the difference. Has everybody here worked with a strain gauge? Who has not worked with a strain gauge? Oh, well, yeah, okay, now, okay. It's good feedback for me, so I know what's worthwhile, what I'm explaining, okay? So, let's look at a strain gauge first, okay? This is a strain gauge. This is what it looks like. It's a material that has a certain resistance. It's a wire. It's embedded on some kind of a Kapton foil or some kind of a polymer, okay? And it has a certain resistance. Now, if you try to stretch this resistance changes very large. So you read the resistance, and your resistance is proportional to your strain, okay? It's a very simple thing. It's a very simple device. It's a very cheap device. Everybody should be measuring strain, and it's made in India, okay? This one especially, this you see here, and it's cheap. You can buy it. So you buy one of these things, and then it comes with the special glue. It has to be glued on the sample. It can't be any glue. It has to be the special glue because the glue has to be stiff. Otherwise, if the glue is elastic, your sample will be under strain if you change the temperature or apply a magnetic field, let's say, but the strain gauge won't see that. So you have to ensure that the strain gauge is well packed in there, okay? So the rest of the measurements, anybody who can measure resistance can also measure strain, because when you're measuring strain, you're measuring resistance again. You just take it and put it, okay? Do it. So what you do is, this is basically this. So you have something, you have a sample like that, and then you connect your wires. You supply a current, and you measure the voltage, and you have your resistance, and you have a calibrated table. And you get some very, very interesting information out of these things. So let's look at the information that we get out of these. What kind of information do we get? So here we have the strain under magnetic field. We take a nickel manganese gallium single crystal, and in this case it was a single crystal. You can take a polycrystalline material as well, but I mean here you can see the anisotropy in the strain. And you glue your strain gauge on your sample along a certain direction, and then you start measuring the strain as a function of temperature, okay? Now, if you don't have a magnetic field and you are in the austenite state at around, what is this, about 295 Kelvin, you're in the cubic state, and you just change the temperature, what you find in nickel manganese gallium in the shape memory alloy is that when you go through the transition, it wiggles around here and things, there's very little change, and it goes down. If you come back up again, you have the reverse Martensitic transition with the little hysteresis here, and it goes back up again. In the event that you apply no magnetic field or anything. Now this has an important implication. If your length is not changing, the length in change, I mean, assuming that the system is isotropic, in the sense that it's okay, it's cubic, and your length change is also associated to your volume change, you find here that the dimensions, when you're going through the Martensitic transitions, the dimensions of the sample is not changing. That is, the atomic volume, or the volume per atom per unit cell, is not changing. There's no volume change. Okay, but what do we have if we apply a magnetic field? So here, a magnetic field of about 1 Tesla is applied when we start the measurement at high field. And then suddenly there's this great big drop. Okay? And then when we go back up again, and then we have this sudden increase again when we measure in the magnetic field. Now, why is this dropping? Now remember from the previous slide here that when the c-axis is the short direction and the a-axis is the long direction, okay? So when we cool this thing through a magnetic field, we are giving a preferential orientation of the we're selecting more variants which have an easy axis along the field direction. An easy axis along the field direction means that the short axis is along the field direction. Here the short and long axis, they all average up. Here we have selected the short axis to be along the field direction, and the strain gauge is so mounted that the strain gauge measures the length change along the field direction. Okay? So along the field direction, we have a decrease in the length. Okay? Is this clear? So we have our decrease. We can see this in nickel, manganese, gallium. Now, if we go to nickel, manganese, tin, and nickel, manganese, indium, what happens? What kind of information can we gain from these strain measurements? This is a similar experiment. This is our reference in the sense that we can understand what this drop is. So we look at nickel, manganese, tin. Let's look at the 0 Tesla data. Okay, there's no field. This comes down, it drops, and then it goes back up again. Okay, it's just like this one. If we look at nickel, manganese, indium, it's also the same thing in 0 field. It goes back, and it goes back up again. Now, when you look at this, you say, okay, I mean, this looks like nickel, manganese, gallium. This also, everything's okay. But look what we have here. If we increase the field, in the case of nickel, manganese, tin, we see that this length change that we have over here under 2 Tesla has now increased. If we go to 5 Tesla, it's increased even more. Here, we see that in 0 Tesla, the difference is largest, and when we apply a field, it's now getting smaller, and then in 5 Tesla, it's even smaller. So we have the opposite effect. Now this was very surprising. Why should we have the opposite effect? What are these data telling us? It took us, well, by the time we got this measurement and this measurement, there were several years in between, and it took us some while to try to give an explanation for this. Now the strain measurement, you see here, is not going to tell you what is happening perhaps microscopically, but it has immediately shown you here that something with the dimensions are wrong, and this has to be explained, why things are like that. So, what apparently seems to be happening is that in 0 Tesla, you're coming from the cubic to the Martensite state, and you have a certain change. When you apply a magnetic field, and if the length change is changing, then the only thing that can lead to length changes in a magnetic field is the selective orientation of the variance by the magnetic field. So the magnetic field chooses a certain axis which is favorable to point in its own direction. So if your easy axis is a short axis, then when you apply a magnetic field along the then when you apply a magnetic field, if it is getting longer, then the short axis should be rotating out of the magnetic field. Yeah? The long axis should be going into the magnetic field. So in the case of nickel manganese tin, what is happening is that, okay, here we have something that is getting, the difference is getting longer, is larger, meaning that if the difference is getting larger, then the short axis has to be pointing in the field direction. More and more short axis has to be growing in the field direction. If I increase the field, then the field is preferring the nucleation of short axis in its own direction, so that the if you have a strain gauge, the strain gauge is in the plane of the sample and it's along the magnetic field, and if the difference is getting larger, then the short axis is growing in the field direction. Okay? Now when we come to nickel manganese indium, the case is the opposite. Let's try to visualize this over here. So we have a cooling field. It is 0. If our long axis is the easy axis of magnetization, then this can be represented by a tetragon, let's say, by a rectangle with this L in this direction. And a short easy axis would be represented with such an arrow. Now, when we apply a field in this direction, this gets longer. Okay? This gets longer, and because we're selecting the easy axis to go along the field direction. If the short axis is the easy axis, then the short axis will turn around in the easier direction and will have a length change in this direction, a longer change in this direction and a shorter change in this direction. Now let's try to see that from the data again. So let's look at the case of the short easy axis. We have an initial length of L, and then when we go to the new phase, this is the cubic phase, this is the tetragonal phase. When we go to the new phase, we will grow variance more in this direction, in the short axis direction, so that this direction will then be shorter. Now, in the case of nickel manganese tin, we are getting a large change along the field direction as we increase the field. So as we increase the field, what is happening is that this is getting shorter and shorter, so the difference between this and this is getting larger and larger. Okay? So in the case where we have a long easy axis, okay, this is our cubic state, and this is the tetragonal state. We have a small change first in no field. If we increase the field, this gets longer, and if we increase the field more, the difference gets here larger in this direction, so that this tells us that in nickel manganese indium, our axis is most probably, the long axis is most probably the easy axis of the magnetization. Okay? And in nickel manganese tin, it is the short axis that is the easy direction of magnetization. So, this is a little bit difficult to grasp, so we'll go over this again. Okay? Now, we have two measurements which are showing us two different things. And we have the case of nickel manganese gallium where we know what's going on. When the short axis grows in a magnetic field, then the short axis growing in the magnetic field direction means it's getting shorter along the field direction. When we go here, we find two opposing cases. So the change over here is small, and when we apply a magnetic field, the change gets larger. When the change gets larger, it means that we're making the sample, the easy axis of the magnetism, we have to make the sample smaller to have the change large. In the case of nickel manganese indium, we have a certain change when we have no field. We have a large change when we have no field, and when we apply a field, we have a change that is getting smaller. So initially, we have, if the change is getting smaller, then we should be pointing longer easy axis in the field direction in this case. And when we do that, we get data that looks like this. What I want to say over here is that when we have, when we measure the strain, what we get indirectly is some kind of an information on a magnetic property. And this magnetic property is the magnetic anisotropy. So the easy axis means that you're dealing with the magnetic anisotropy. So the length change under various magnetic fields at phase transitions can give you information on these on which direction should be the easy axis. These are the kinds of measurements which we can do and play around with. Now, this, I can see from your faces, is kind of difficult, yeah? But it's very important in that sense. So, has anybody understood this? Yeah, that's good, okay. It's, it is, in a sense, somewhat confusing, but okay, anyhow. So, I'll probably come back to this, but I'll get your minds off this for the moment. Yeah? In the next lecture again then. So now there is another phenomena which is important that tells us what kind of magnetic interactions we have in our system, and that is the so-called exchange bias effect. Now, exchange bias is observed when you measure a magnetization, and the magnetization curve looks like this. This is a simplified version. So you have normally a magnetization curve, a hysteresis curve, is symmetric around the origin. Well, sometimes under certain conditions, when you measure the magnetization loop, what you come across is a loop that is shifted to negative values, in some cases to positive values, and in some cases you can also have vertical shifts of these things. Now, what does this mean? When we observe a shift like this, what do we understand from this? The width of the hysteresis loop tells us what the coercive field is. That hasn't changed. So half the width of the magnetization loop is the coercive field. The shift from the origin of the hysteresis loop from the origin is called the exchange bias field. So this we find when we have mixed ferromagnetic and anti-ferromagnetic interactions. We have this in a system if we grow two films on top of each other. This is the easiest way of looking at it, actually. We have, let's say we have an anti-ferromagnetic film grown and a ferromagnetic film that are grown on top of each other. This has a certain Néel temperature and this has a certain Curie temperature. And we select the material such that the Néel temperature is lower than the Curie temperature. And we're sitting here at a temperature between the Néel temperature and the Curie temperature. So the antiferromagnetic part is disordered, but the ferromagnetic part is ordered. So if we cool this down through the Néel temperature, under a magnetic field, we preserve the orientation of the ferromagnet, and the antiferromagnet grows on top of that. Now, we start out with a sample like this, and now we are, since we've cooled it in a field and we're measuring the magnetization, our starting point is at this field over here. So when we're cooling this in a field, what we're doing over here is that at this interface here, it looks as if we have an uncompensated antiferromagnet, yeah? We have a layer of spins looking in this direction and a layer of spins looking in the other direction. So this layer here pins this layer here. It holds it. It's like having a spring between them. So now when we start decreasing the magnetic field, first nothing happens until we get to a point where these spins begin to rotate in the opposite direction. Normally, it should have started pointing in the opposite direction at the moment when the field was reversed. But that is not the case. What we see over here and what happens is that these layer pins this layer, so these things have difficulties in turning. But eventually, as we increase the field more negatively, they turn around and you come to a certain point. But these are still strongly coupled to one another, so that when we start reducing the field, what happens is that these spins rotate much easier in their reverse to their original position than as they originally rotated initially in the other direction. So we have a system where it is difficult to make the magnetization rotate, but once they have rotated, then it's easier for them to come back. It's like having a spring between the two layers. Okay? So this is the exchange bias effect. If you see an exchange bias effect, you have to have some kind of an antiferromagnetism somewhere. This is the idea of the thing. Okay? It's important in this sense that when you're measuring complex systems and things, you've measured the magnetization and so on, and then you go down to low temperature, and then you cool it in a field, and you measure something, and if you see shifted curves, then you can be sure that you have some kind of an antiferromagnetism in there. So now, we talked about compensated antiferromagnetic surfaces and uncompensated. So if we look at these layers that are here in between, from the top, what we can see is we can either see this kind of an order or we can see this kind of an order. This is compensated and this is the so-called uncompensated. Now it turns out that whether it is compensated or uncompensated, there is not much effect on the exchange bias effect. So these pictures over here, of course, they're only meant to be sort of well, they're only schematic, let's say. I mean, they may not, of course, represent the real case. The real case is the measured case. What happens when we measure the magnetization as a function of field? We can do this in two manners. So what we originally did was, when we were at high temperature in the ferromagnetic state, and the antiferromagnetic was in the paramagnetic state, we cooled this down through the Curie temperature in a field. You can either cool this down in a field or you can cool it in zero field. There's not much difference. Here we show the two cases. This is for a nickel manganese antimony Heusler alloy, which is also a Heusler, showing similar magnetization properties, similar magnetization versus temperature properties, as for the other systems. So we have here two cases. One is a zero field cooled and one is a field cooled. In this case, zero field cooled and field cooled means that, okay, you cool it in a zero field, you measure the magnetization, and then you're finished with it, and then you go back up to high temperature, and then you cool it in a field, and you measure the magnetization again. If you see here, what happens is that we have shifts in all of these curves over here to the left, which tells us that there is an exchange bias effect going on in these systems. If you cool it in zero field, nothing much goes on. Now, when you cool it in zero field and come down to the temperature, these are all measured at 5 Kelvin, the place where you're sitting is here. You're at this point over here. And when you measure the magnetization up and down, it's symmetric about the origin, because there is no preferred direction given to the coupling between the ferromagnetic and the antiferromagnetic. It's only when you cool it in a field, then your ferromagnetism is given a preferred direction, and so to switch the ferromagnetism from one direction to the other direction requires a larger field when you're decreasing the field than when you are actually increasing the field. And this is the case for many different compositions. These kinds of measurements tell us that in our Heusler systems, that where we have various kinds of magnetization curves over here, that the states at low temperatures do indeed incorporate an antiferromagnetic part. So we now know that we have antiferromagnetism at that point. Okay? So we haven't measured yet we haven't done a measurement that will show us the antiferromagnetism directly as yet. We have to do that, of course. But these experiments alone, they tell us that we do have some kind of an antiferromagnetism. So I'll come back to the strain problem later on, but what happens is that these kinds of measurements are helpful, the strain measurements are helpful in identifying what kind of an axis, a long axis or a short axis, is the easy direction of magnetization, and the exchange bias effect tells us whether we have intrinsic antiferromagnetism sitting there or not, which we cannot detect directly from the measurements. Okay? So we'll take the break now. Are there any questions? Yes.
This is a slightly research-oriented question. Can we expect exchange bias if we have an interface of two different types of antiferromagnetic material? I mean, if there is an interface between G-type, A-type antiferromagnetism and with different nil temperatures. Mm-hmm. So in that case, in principle, can there be exchange bias?
Well, if you have an antiferromagnet, two antiferromagnets on top of each other, and if you measure the magnetization, you're going to get a linear response. So the magnetization versus field will be linear. Okay? What the details of these linearities will be, I don't know. How the interfaces will couple, I don't know that. Definitely, of course, if you say that you have two antiferromagnets with two different nail temperatures, I would expect that something would be going on, but I don't know. But you won't see an exchange bias in the sense that you see over here, because this is a ferromagnetic response. Yeah, you're looking at a hysteresis curve, which you cannot find in an antiferromagnet. It will be just linear. And you probably will see something, but I don't know how you would see that in the magnetization.
Yeah, actually we did with our material. So in that case, we could see higher magnetic moment. There is an increase in magnetic moment. We did all other measurements, including neutron diffraction also. So it is confirmed that the magnetic moment is higher. And then our explanation was that it is something that excess magnetic moment is coming from the interface of these two antiferromagnets. Yeah. Because the interface will not behave in either way. So in that case, there will be some, the magnetization cancellation will not be there. So we should expect some higher magnetic moment. Okay. But I'm not sure if it will show exchange bias or not. But higher magnetic moment is there.
I understand. So that you have uncompensated states which are parallel, you can get a magnetic moment. Okay, okay, I understand. But I mean, I don't know whether you would get an exchange bias or not in that case. Any other questions?
So in that graph of strain versus temperature, when we measure this strain, I think we measure it on a bulk material.
We measure it on a bulk material, that's right.
Before this, previous to this. So like, how do we know that the strain is along 001 axis? How do we confirm that?
You have to mount your strain gauge in that direction. So this is your strain gauge, and you have a sample underneath this. Okay, you can't see the color here. There's a sample here, but the color has disappeared. So if you visualize a sample down here, this is mounted on a sample, which is a square here, but I can't see the color. Okay, so you have to know which direction your crystal is oriented, and you have to place your strain gauge such that the measuring direction of the strain gauge coincides with the axis that you want, so that you know that you're measuring the strain along that particular direction.
Yes, then what is causing the hysteresis? The strain and the variation of strain is along the same axis. So what is actually causing the hysteresis?
This hysteresis here, you mean? Yeah. Okay, I mean, this is the Martensitic transition. The Martensitic transition, you'll see a hysteresis in whatever you measure. Okay? So this is the, these arrows here show the Martensite start, Martensite finish, this austenite start and austenite finish, almost. Okay? So that is telling you what the strain, that is the hysteresis itself. The strain, this is a polycrystalline material, so it only matters when you're measuring in a magnetic field that the strain gauge is mounted parallel to the magnetic field direction. You can also mount it in the other direction. But here we measured it along one particular direction. Okay? And and we get these different responses when we measure these.
And usually the area in the hysteresis always indicates some loss.
Yes.
So in this case, what kind of losses?
Well, loss is associated if you want to do some work using the phase transition. This loss, if you're going through the phase transition, let's say adiabatically, then you have a loss in the sense of heat. You have dissipation.
Loss would be the loss of heat.
Yes.
Area would be.
The area is the area of the hysteresis is associated with the energy related to the transition. So whatever you have here, the latent heat, and that is your loss. You have to pay for the latent heat. Okay.
In that figure, it is decreasing in the y direction. So its length is decreasing.
Yes.
But in above, both are increasing.
Yes.
So how?
Yeah. Okay. That's what I tried to explain, and I couldn't. I want to do that again. Okay. Let me try again. So, in the next slide here. Okay. Here you are in a cubic state, and here you are in a tetragonal state. So, when your field is 0, you are originally in this state. Okay? When you apply a magnetic field and cooling it through the transition, what are you nucleating? Let's ask the question like that. You will nucleate variance in the field direction, or you will nucleate variance that have the easy axis in the field direction. Your easy axis can be short, or your easy axis can be long. So, if your easy axis is long, is your sample going to, is the difference in the length going to increase or is it going to decrease? So, if this gets longer and longer if it gets longer and longer in the field direction, then the difference is going to get smaller and smaller. So you have the case of nickel manganese indium. If your easy axis is short and you're going through the Martensitic transition temperature with the field along the strain measurement direction, then you are selecting variants, or you're nucleating variants that have a short axis along the field direction. And if you have a short axis along the field direction, the more higher field you apply, your sample will get shorter and shorter, and that will mean that the difference will get longer, the difference will get larger and larger. I think I explained that a little bit better now. I'm not sure. We'll come back to this, but is this okay now? Is it better? So we'll have a break. What I'll do right now is I'll go back to the strain problem again. We'll go over it again so that it is more clear on what is going on. And after that, eventually, I want to go into the magnetocalorics, but I won't do that today because it's going to get all mixed up. So we'll try to resolve this issue with the strain problem. Okay? I'll give you some more examples on these, and then that will be fine for today. Okay? And then we can continue with the magnetocalorics and things like that as of tomorrow then. Okay. So let's get back to this figure. Let's compare here the various cases. So we have nickel manganese gallium, nickel manganese tin, and nickel manganese indium. First, we measure in zero field. Nickel manganese gallium, nothing happens in zero field. It just goes down and back up again. There's some wiggles around the transition. In nickel manganese tin, in zero field, we see that there is a decrease. So it appears that the length is getting smaller in the Martensite state. And the same thing is true for nickel manganese indium in zero field. So here we have a decrease, and here we have also have a decrease. Now, we start here. What does this decrease tell us? Now, in the case of nickel manganese gallium, we have a single crystal. And we know from other measurements that in our single crystal, the C-axis in the Martensite state is the shorter axis. Okay, we have a short axis as the easy axis. The easy axis is the short axis. Whether it's C or what, we don't care. The short axis is the easy axis. So what happens is that when we apply a magnetic field, we are, in the case of nickel manganese gallium, when martensite nucleates and starts to grow, the twin boundaries are very mobile, so that when we apply a magnetic field, the variance with the variance that have an easy axis when we're cooling in a magnetic field, variance along the easy axis will be selected. Okay? We're cooling in a magnetic field. What does a magnetic field do? It selects the easy direction. The easy direction is a short axis in the case of nickel manganese gallium. And we have this decrease in the length. Okay. So this is our reference of the measurements. This could have gone up. It doesn't go up. It goes down. It goes down because the field selects the easy axis, and the easy axis is the short axis. So here, what happens? We see one further thing, that in a magnetic field, these arrows point to the Martensite start temperatures. In a magnetic field, this Martensite start temperature moves down and down to lower temperatures. In both cases, here also and here also. Okay? So then, here we apply a magnetic field. The Martensite transition temperatures has shifted down here. And what has happened? This change in the length, the relative change in the length got larger. When we increase the field, the change in the relative length also got larger in the relative length change. Okay. So when we go to nickel manganese indium, the opposite has happened. When we apply a magnetic field, it got shorter and shorter. Now let's go back and take another look at this. As we say, we have two cases. The cases are, if we have a easy axis as a long axis, it's quite unusual, but it can happen. If we have an easy axis as a long axis, what would happen to it if we apply a magnetic field? Now, we are applying the magnetic field here at high temperature. The magnetic field is constant and we're cooling. As we cool, we go through the Martensitic transition temperature. As the martensite starts growing, if we didn't have a magnetic field, they would grow in all sorts of random directions. Okay? But when we have a magnetic field, then the magnetic field is selecting the easy axis for the nucleation direction. Okay? Martensite is nucleating somehow. And if the magnetic field is influencing this nucleation, during the nucleation process, it is choosing the easy axis as the growth direction along the magnetic field. So, now, if your long axis is the easy axis, then along the field direction, what is going to happen to the sample? It's going to, the difference between the initial and the final state is going to get larger. Okay? And, sorry, it's going to, when the easy axis grows along along this direction, then this length is going to get larger. So the difference between this case and this case is going to get then, according to this, what we over here, this difference is going to get smaller and smaller because you are nucleating things in the longer direction. Here it is long, here it is short. If you're nucleating things in the longer direction, here it is long, so that it remains long, and the difference is smaller. Here it is long, it is in the austenite state, and applying a magnetic field, here it is remaining long. So the more and more the magnetic field increases, the difference between these two become smaller and smaller. Okay? Because it's remaining long. I'm growing things, I'm growing longer entities in the field direction. I'm making it remain long. Now, if the short axis is an easy axis, then when we cool through the Martensitic transition temperature, if the field is influencing the nucleation process, then it will nucleate martensite variants that have a short axis along the field direction. So then as I increase the field, I am making it shorter and shorter and shorter. With respect to what? With respect to the initial state. So here it was long, then it became short because I have components along the magnetic field that are in the short direction. But here, if I'm influencing the growth of the martensite along the field, which selects the shorter length, then I'm making the difference more and more. Because here it was long, here it has now become even shorter because I've selected more shorter components along the field direction. And here, I've made it even shorter. Okay? So this difference has increased even more. Now, these were all assumptions, of course, that the easy directions are short directions and long directions are short directions, actually. But this assumption and this are consistent. That is, the magnetic field, apparently, from this data, number one, the magnetic field apparently influences the nucleation process somehow. That is true. Because if the magnetic field did not influence the nucleation process, then all these curves would have been similar. There would have been no change. And depending on how it is influencing the nucleation process, either by selecting a short axis or a long axis, then we have these two kinds of behavior. So at the end, what is the strain measurement telling us? These kinds of strain measurements. They're telling us something very indirectly and something very unexpected, that as a result, we can give an argument on the easy direction of the magnetization, that is the magnetic anisotropy direction, not the magnetic direction, of course, but in which plane the magnetic anisotropy is the highest, just by looking at these. So at the end, we say, okay, then our short axis is an easy axis, or our long axis is an easy axis. Now, what is a short axis and what is a long axis, we don't know. I mean, which axis is that along the crystallographic direction? In the cubic state, okay, it's pretty easy to conceive. But once we go into these complex modulated phases and things like that, then what is the short axis? What is the long axis? That we don't know. But these measurements are telling us definitely that the field is influencing the nucleation process, and it is selecting out the direction in which the easy axis lies, in one sense. Now, these are quite some differences, and we know that there were some, we've applied fields in the order of 5 Tesla, and we know that there are quite some large differences in the magnetizations of nickel manganese gallium and nickel manganese tin. Okay? In nickel manganese antimony, this is less. For some reason or another, the change in the magnetization at the Martensitic transition is not that much. It's practically like in gallium. In gallium here there's a jump. In antimony here there's a jump. Okay, in gallium it's less, but in antimony it's also not that much. So how would this reflect in the strain measurement if we measure the strain in nickel manganese antimony? And well enough, you see here that the situation is not like as in nickel manganese tin and nickel manganese indium, but rather this nickel manganese antimony looks more like nickel manganese gallium in one sense. The relative length change is very small. There is a shift of the transition with changing field. These are done for 2 different compositions. You can see both of them. And what you see here is that the change in length is not much different for the both. And here also, you see that whether you measure in 0 Tesla or 5 Tesla, here there doesn't seem to be much difference. So the field in this case, for some reason or another, it could be due to the magnetocrystalline anisotropy, that here there is not much influence of the field in selecting any preferred orientation for the growth of the martensite. Okay, now this is basically all what I can explain concerning strain measurements and what we can extract from the strain measurements. And I want to leave this here, and I don't want to go into magnetocaloric effects now today. It won't make any sense. Please, if you have any questions, please ask. Do you have any doubts, any questions, anything in mind that you would like to ask here?
I will just say what I understood.
Good.
Please correct me. As I understand, this is the entire thing is a interplay between 3 or 4 kinds of energy. One, I can say exchange energy, anisotropy energy, then there is a magnetostriction energy, and probably domain wall energy maybe. So there is an interplay between these different kinds of energy, and the sample will behave which one dominates the other. So accordingly, I think the behavior of sample will change. So is that correct, or there are some other kinds of energies also involved?
Well, okay, let's take it one by one. If you're looking at the magnetic field-induced transformation, when you're going from one state to the other state, okay, you're applying a magnetic field. When you're applying a magnetic field, you have an exchange with the magnetic moment. Now, if you didn't have a magnetic moment, the magnetic field wouldn't do anything, and nickel titanium, it doesn't do anything. Yeah? So you need the magnetic moment. So you're first interacting with the magnetic moment. And due to this interaction, through the magnetocrystalline anisotropy, you are giving a preferred crystallographic state. You need the magnetocrystalline anisotropy there, and you need the exchange, of course. So you're applying a magnetic field, you're interacting with the magnetic moment, and you're supplying energy with the magnetic field, and you're giving rise to a transformation. Okay, so that would be the energy supplied by the magnetic field to overcome the latent heat. So now, if you're talking about the strain process, in this case, it is again an interaction between the magnetic field and whatever is growing. So in the beginning, you have a cubic ferromagnetic state. You're applying a magnetic field, a large one or whatever, you're saturating it, let's say it's in saturation, and then now you're going to grow martensite. The martensite state is a magnetic, these are complex state, but when you're applied a very large magnetic field, you do induce some kind of a ferromagnetism. So when you're when you apply 5 Tesla and cool it in a magnetic field, you're going to interact immediately with whatever is going to grow. So the energy over there that you are supplying with your magnetic field is providing a strain in a particular direction. I don't know what kind of energy you would call this, but the energy supplied by the magnetic field would be going in there to overcome the strains that are all around so that they grow in an energetically unfavorable direction, because the favorable direction is random. Yeah. I don't know whether that is answered, but...
Yes, that's
Okay.
that's what I understood.
Okay.
Tomorrow we'll go into the magnetocalorics, second order transitions, the subtleties in second order transitions and things like that. Okay?